Hello, so today I'm going to show you how to derive quite an important equation to us as mathematicians, and that is de Moivre's theorem. And de Moivre's theorem is for complex numbers, so at least in the WJC syllabus you'll only come across it in further maths, and incidentally you come across it in FP2. Now I'm going to go through a proof with you. It's shown up in quite a few of the past papers and it's part of the syllabus, so it's quite important that you're able to derive the formula as well as use it and then apply it to trigonometry and whatever else we decide to use it for. So de Moivre's theorem is written as cos theta plus I sine theta all to the power k in whatever kind of brackets you like, but I like curly ones, well, curvy ones, is equal to cos k theta plus I sine k theta. Though usually we write it with n's. Now, the way we're going to prove de Moivre's theorem is through a method called induction, that if you are doing the syllabus you would have done in FP1. It's a really nice, clever little proof, and this one especially is quite nice. So traditionally in induction you'll show the result is true for the smallest integer that you're trying to prove it from, and then you'll just assume it's true for any given number, and then you try and prove it for k plus 1, so any given number like plus 1. So if we proved it for 1 and we proved it for k plus 1, then we know the result's true for 1, but it's also true for 1 plus 1, which is 2, and 2 plus 1, which is 3, and 3 plus 1, and so on and so forth, all the way up until you've proved it to infinity. So what we're going to do is we're going to start by writing out the result we're after, and that is cos theta plus I sine theta all to the power of k plus 1. And we're trying to prove, so I can't technically put this equals sign here yet, but what we're trying to prove, and I'll put these little funny square bracket things here to show that, is that that is equal to cos k plus 1 theta plus I sine k plus 1 theta. So we can't use this result in our calculations. That's what we're working towards. So if we're going to start with our cos theta plus I sine theta all to the k plus 1, we need to remember our laws of indices, which says that this is equal to cos theta plus I sine theta all to the power k multiplied by cos theta plus I sine theta to the power 1. And one of the handy little things that we get from induction is that when we've shown the result to be true for k up here, we can then take this part of the formula, which is cos k theta plus I sine k theta, and just stick it in right here. It'll obviously make the proof a lot easier for us, and this is the general trick that you do with all proof by induction at some point. So here we have cos k theta plus I sine k theta multiplied by cos theta plus I sine theta. And so now we just have to multiply these brackets out. So we can use FOIL, so the first terms, so that's cos theta cos k theta, sorry. So cos theta cos k theta, O outside, so plus cos k theta I sine theta and now I, the inside, plus I don't know why I'm going through this, you already know this, multiplied by cos theta. Oh, and that's gone off the camera. And now this last one is a minus because we have I, and that's the basic rule of what complex numbers is, that I squared is equal to minus 1. So minus sine k theta sine theta. And so if we now gather our positive and our negative terms, no, our real and our imaginary terms, I'm very sorry about that, not quite the same thing, we're going to get cos theta cos k theta minus sine k theta sine theta plus I, and then I'm going to put in brackets cos k theta sine theta. Again, it's gone off the camera, sorry about that. Plus sine k theta cos theta. And so if you recall your double angle formulae, which in WJC we've learnt in Core 4, you can see that this result here is equal to, well, if theta and k theta were a and b, it would be cos a plus b. So cos minus sine is cos a plus. So what we get here is cos our a is k theta plus theta plus I, and this side here, this is the sine formulae, so we get here sine a plus b because it's a plus there. So what we're going to get in the end is I sine a again, which is k theta, plus b, which is theta, and then we can factor theta out as a common factor, so we get cos k plus 1 theta plus I sine k plus 1 theta. And as you can see, that is the result that we were looking for up here. And so we've now proved the result for k plus 1. If you don't believe me about 1 being true, cos theta plus I sine theta all to the power 1 is just cos theta plus I sine theta, and cos k theta plus I sine k theta is again cos theta plus I sine theta, so it is true for 1, and it is also true for k plus 1, assuming it's true for a value, which it is. And so now we've proved de Moivre's theorem all the way up to infinity from 1. Okay, thank you.